Look at a car windshield. It's angled outward, sloping away from you if you're inside. Airplane cockpit windows do the same thing, angled like this mainly for aerodynamic and glare reduction. Now look at a ship's bridge windows. The windows tilt the opposite way, inward at the bottom, towards you. And if you've ever noticed an airport control tower, it uses the same design. That's not a design quirk. Ships face completely different visibility problems than cars or planes. And the bridge window design, the angle, the size, the wipers and the heating systems is built around solving these problems. The bridge is the command center of the ship. Officers navigate from here, monitor traffic, control the engines, communicate with port authorities and coordinate the crew. For all of that to work, they need to see. Not just ahead, but in every direction. According to SOLAS, the International Convention for Safety of Life at Sea, there are specific requirements. For ships of 55 meters or more in length, constructed on or after July 1st, 1998, officers must have unobstructed sight from dead ahead to at least 22.5 degrees abaft the beam on both sides. That's more than 180 degrees of horizontal visibility. The view of the sea surface forward of the bow must not be obscured by more than 2 ship lengths or 500 meters, whichever is less from the conning position. This is also why you see some ships' bridges moved forward. All of this means large windows, and lots of them, wrapping around the entire wheelhouse. But a window covered in glare, rain, ice, or condensation is the same as no window at all. Bridge windows are angled inward at the bottom. If you're standing inside the wheelhouse looking out, the bottom of the window is closer to you than the top. This is the opposite of car windshields and aeroplane cockpits, which angle backwards for aerodynamics. Ships don't need aerodynamics. Wind resistance on the superstructure isn't the problem, glare is. When sunlight hits flat vertical glass, it reflects straight back at whoever is standing inside, bright enough to make it impossible to see through the window. Angling the glass changes where that reflection goes. Instead of bouncing back at eye level, it deflects downward, out of sight. The same principle applies at night. Instruments, displays, overhead lights, all of it can bounce off flat glass and create ghost images over the view outside. Tilt the window and those reflections are directed downward rather than back at eye level. During bad weather, rain runs off faster too. On vertical glass, water clings to the surface. On angled glass, gravity pulls it down more effectively. And when the ship is moving, airflow helps push it off. The combination keeps the glass clearer in wet conditions. It's a small angle, usually 10 to 25 degrees from vertical, but the effect on usability is significant. Officers also need to see down. During docking and mooring operations, officers need to watch lines being handled on deck, see fenders against the pier, judge distances to other vessels. The bridge wings extend outwards specifically to provide sightlines straight down to the ship's side. Even with angled glass, rain still accumulates. That's where this familiar system comes in: wipers. They work on the same principle as car wipers, built for harsher conditions. Salt spray, continuous winds, heavy weather that doesn't stop for hours. These wipers operate at variable speeds depending on the conditions. Light rain, slow sweep. Heavy weather, continuous fast motion. On older vessels, the officer on watch changed the speed manually. Modern ships use automatic rain sensors that adjust wiper speed based on how much water is hitting the glass. But wipers have limits. In extreme conditions, the spray is often too dense and too constant. No wiper blade can keep up. The water wins. So, engineers added something else entirely. Look at the center of some bridge windows, and you'll see a circular disc about the size of a dinner plate. It's called a clear view screen. The disc spins at high speeds, typically between 1,000 and 3,000 RPM. As it spins, centrifugal force throws water off the surface before it can settle. Rain, spray, even ice buildup gets flung away before it can obscure the view. Clear view screens came from naval technology. Warships needed reliable visibility in combat conditions, where even a few seconds of impaired vision could be catastrophic. The technology proved so effective that merchant ships adopted it. It's simple: an electric motor, a spinning disc, and as long as the motor runs, the screen stays clear. In the worst conditions, wipers are overwhelmed, and the rest of the windows are streaked with water. The clear view screen gives officers at least one small circle of unobstructed visibility. That's often enough to see critical information: navigation lights, other vessels, shoreline features, or buoys. At night, the visibility problems change. During the day, officers fight glare and rain. At night, they're trying to see objects that aren't lit. Unlit buoys, small fishing boats without proper lights, debris in the water, or distant shorelines. The human eye can adapt to darkness, but it takes time. One moment of bright light resets it completely. So, bridge lighting at night is designed around one goal: don't destroy the crew's night vision. Red light is the standard. Red lights allow officers to see instruments, charts, and controls without affecting their ability to see outside. The wavelength of red light doesn't trigger the same response in the eye that white light does. Window coatings help reduce internal reflections too. Some bridges use anti-reflective treatments on the glass to minimize how much instrument light bounces back. Combined with the inward angle, which already deflects reflections downward, the bridge stays dark enough outside to see what's there. Reflections aren't the only thing that can ruin visibility. Even without rain, cold weather creates two problems: condensation on the inside of the glass and ice on the outside, and both destroy visibility. Condensation forms when warm, humid air inside the bridge meets cold glass. The moisture condenses on the surface, fogging the windows. Ice builds up on the outside when freezing rain, spray, or snow hits the glass and doesn't run off. Ships operating in northern waters or during winter need heated windows. The most common solution is electrical heating elements embedded in the glass, thin wires or conductive coatings that warm the surface when powered. Some systems use warm air blown across the inside of the glass, similar to a car defroster but on a much larger scale. The heating has to be powerful enough to melt ice, not just prevent condensation. Ice buildup can be thick, centimeters in severe conditions, and it doesn't melt easily. If the heating system can't keep up, officers lose visibility and have to rely on whatever small section remains clear, or step outside onto the bridge wings where there's no glass in the way. Defrost and heating systems are treated as critical equipment. If power has to be rationed, they stay on. Yes, the technology exists. 360-degree cameras, night vision, thermal imaging, high-resolution displays. You could, in theory, remove the windows entirely and navigate from screens alone. But regulations require direct visual observation. SOLAS mandates that officers must be able to see with their own eyes, not just through screens. There's a practical reason for that, beyond regulation. Cameras fail. Salt spray on lenses, power interruptions, vibration, and the human eye is still better at depth perception, detecting motion, and judging distances. Officers do this instinctively through glass. Through a screen, it takes longer, and longer is dangerous. There's also trust. Mariners want to see the situation themselves and not rely on a screen's interpretation of it. Windows remain the primary system. Everything else is backup. Every feature of a ship's bridge windows exists for a reason. The angled glass deflects glare and helps rain run off. The wipers handle what gravity can't. Clear view screens provide a last resort circle of visibility when everything else fails. Bridge wings give officers sight lines they can't get from the inside. Red lighting and dimmable controls preserve night vision, and heated glass prevents ice and condensation from blinding the crew. None of it is arbitrary. It's all solving real problems that show up when you're navigating in the middle of the ocean, in weather, at night, in traffic, or during docking operations. The design has evolved over the decades. Better materials, better coatings, better systems. but the core principle hasn't changed. Officers need to see clearly, in all conditions and at all times. That's why every detail of the ship bridge windows look the way they do. Hopefully you've enjoyed this video. Subscribe if you'd like to see more. Until next time, thank you for watching.